All right, in this video, we're going to take a brief look at just a couple of unique transformation things that happen with exponential and logarithmic functions, things that we haven't seen happen with other functions. So I'm not going into full detail in this video on transformations. We did a lot of that in the first semester, and there are better places for us to do that later this semester. So, for now, what we're going to look at is I've got a parent function y equals 2 to the x in the dotted line here in red, and then we have a solid blue line that is a transformation of that. Okay, it's maybe a little bit harder to see these things, so I've highlighted some points along the way, and we can see that this point, for example, is at 2 comma 1/2. This is a point at 3 comma 1, and this point is out here at 4 comma 2. Our red points from the parent function, right, this is the -1 comma 1/2, 0 comma 1, right, 2 to the 0 power is 1. All right, and then we see the point at 1 comma 2. Right, and those are our parent function points for an exponential with a base of 2. And so looking at this, then, we can kind of see what is going on here. It looks like a horizontal translation of about 1, 2, 3. So the description here, what's happening is we are horizontal. And we don't even have to say that. It's just it's a shift right 3. Right? So from our parent function, representing this with the arrow diagrams, like I like to do, the parent function, here's the 2 to the power. This is a shift right, which is a horizontal transformation, so that puts an arrow down here. And right is the positive side of that axis. And so to build this function, if we start here with an x, then we need the inverse operation to adding 2, which is subtracting 2. So the equation starts with the x, subtracts 2, and then that gets put into the exponent. And so that blue graph should be y equals 2 to the x minus 2. And we certainly would be able to check that with some of our numbers there. Okay, except, oh, it's shift right 3. So it should be a plus 3 and a minus 3. Okay, I was having a panic attack there for a minute. Okay, not really, I don't have panic attacks. Okay. So shift right 3, and the inverse operation to that is subtracting 3, so we take the x, subtract 3, that should be, the graph should be 2 to the x minus 3 power. Okay? Nothing special there, it's just a single transformation. We're accustomed to doing more than that, but what I want to look at now is the same two graphs, but I'm going to highlight some different points. And based on the points that are in here that we've highlighted, on the red graph again, this is the point 2 comma 4, this is the point 1 comma 2 up here, this is our point 0 comma 1. And so if we're kind of looking at this, it looks like the gaps in these points, if I look at this gap and this, they're not the same size every time, so it's definitely not a shift down. Okay, but if I look at what's happening in the values there, this was at 1, now it's at 1/8. Okay, this was at 2, now it's down here. This is not actually showing that particular point right there, but I grabbed this one out here. It was at 4, and now it's a half. This looks like it got squished down closer to the x-axis. So this is a vertical compression. And the amount of the compression, well, the gap here used to be all the way to the red one. This gap was 1 down to the axis, and now it's 1/8. And this gap out here all the way down to the axis was 4, and now it is 1/2. And so that's like 1/8 as close. If I divide 1 by 8, I get 1/8. If I divide 4 by 8, I get 1/2. If I divide it by 2 by 8, I'd get a 1/4, and that looks like about where that point is. So this is a vertical compression by 1/8. So, describing it that way, I have my parent function 2 to the power, and this is vertical, so that's happening on the output side. Vertical compression by 1/8 means multiply by 1/8. So now if I start my x here in the front, it says put that into the power of the 2. All right, so the x goes into the exponent of 2 on the first arrow, and then the whole thing gets multiplied by 1/8. So this is indicating that the equation of the graph is 1/8 times 2 to the x. The other one says, no, it's 2 to the x minus 3. Okay, well, which one's right? Because these are actually both identically the same graph. They go through all the same points. The answer is that they're both right, and we can see that especially if we focus on this one up here, and we think about our properties of exponents, which say that subtraction in the exponent used to mean that there was some division that was going on. And this was actually equal to 2 to the x divided by 2 to the third. Okay, but what's 2 to the third? Well, 2 to the third, 2 times 2 times 2 is 8. So this is 2 to the x over 8, which is exactly the same thing as 1/8 times 2 to the x. So with this exponential function, what we find is that horizontal shifts are equivalent to vertical stretches and compressions, okay, which is unusual. Okay, we've seen things before where shifts one way are the same as shifts another way, or stretches in one direction are equivalent to compression in another direction. But this is an equivalence between a shift and a stretch/compression. Okay, that's pretty unique. All right, from the logarithm side, I don't know why I put the emphasis on that syllable. In red here, I have the log base 2 of x, so it has all the points that we're accustomed to having at 1/2 comma, let's see, this is the point 1/2 comma -1, okay, and this is the point 1 comma 0, and this is 2 comma 1. And if I take a look at what's happened here, it looks like, again, if I'm connecting these points here, well, this point out here is clearly at 6 comma 1. This point is at 3 comma 0, and that one's labeled there at 1.5 comma -1. Well, it's clearly not a horizontal shift. Let's take a look at the size of the gaps. This gap is 6, whereas this gap horizontally here is 2. This gap from the axis all the way to that point is 3. This gap that is in here is just 1. And we've got a gap over here of 1.5, and the little gap in here is just 1/2. So what's happening, it looks like a horizontal stretch. Everything now on the green graph is 3 times as far away from the x-axis as everything on the red graph. So we would describe this as a horizontal stretch by a factor of 3. And so if I start with my log base 2 function, horizontal stretch by 3 means that that's happening over here, and I'm multiplying by 3, which would kick this one back here as a divide by 3 as the inverse operation. So if I start here with the x, it says take the x, divide it by 3, and put that inside of the log base 2. That's the graph of the green function written in blue. Okay. All right, probably got an idea maybe of what's coming up here next. All right, this one is clearly showing that we should be focusing on these gaps. All right, so let's take a little bit different approach at this. Let's take a look at what we had before, because these are the same functions again. And what we see happening inside of this logarithm is a division, and we know by our properties of logarithms that that division can be written as subtraction. So we should be able to write this thing as the log base 2 of x minus the log base 2 of 3. And so what was in here a horizontal stretch when written as log base 2 of x over 3, we now see can also be interpreted as if we looked at this, we start with the x, the log base 2 of, and then subtract the log base 2 of 3, which is just a number, right? We can look up, we can use our calculator to figure out what that number is. But that is exactly what the parent function right here, the description of a vertical translation, okay? A shift down in this case, and that's what we're seeing over here in the blue, is all these blue gaps are exactly the same size, and the size of them, as it labels in here, is exactly log base 2 of 3. And that's the shift down there. So in a logarithmic function, we also see, and it shouldn't be a surprise because of the close relationship to exponentials, that in this case, our horizontal stretch was equivalent to a shift down. And that, again, is a fairly unique thing to exponentials and logarithms. This was not a complete exploration of transformations. We may ask for a little bit more than that on the assignments in terms of the things that we've done before, but just wanted to point out this unique thing that happens here.